So, welcome back students. We are basically discussing desymmetrization as a useful strategies, and now what I am trying to do will give you a target molecule which is basically a natural product and its structure is this compound. Its name is cuparinone. It is a natural product, and we are saying that this natural product is a terpenoid molecule, sesquiterpene. We see structure, it is basically cyclopentane based compound, cyclopentanone. You have a geminal dimethyl group as well as this carbon you are having a methyl as well as a paratollyl group. Now, the starting material I am not I will be giving to you, but we will be basically trying to do the retro and then the starting material which was given to you is this starting material. This group is basically a paratollyl group. The starting material, if you see, the starting material is a symmetrical starting material, and I say that our strategy will be based on a desymmetrization strategy for the starting material is a symmetrical starting material, symmetrical starting material. The starting material is having symmetrical structure. So, you need to use a simple desymmetrization strategies to access the target molecule. Now, before we come to the retro, which is will give you the entire structural viewpoints, will now let us do the very conventional retro, that how this molecule can be constructed. So, I say if you having a this particular ketone as an intermediate, you can do a simple FGI to put two of this dimethyl, gem dimethyl by successive alkylation. Now, this particular alpha beta unsaturated ketone, you can think about that how this can be constructed if you have a compound like this. Now, just the earlier lecture we talked that you can create a alpha beta unsaturated olefin adjacent to a carbonyl by a selenium based chemistry. So, if you can do a selenium based chemistry, you can introduce a pH ACCl as a electrophilic reagent. Now, here the point is, if your starting material is this, phenyl selenium chloride is a quite bulky group. So, we expect that once LDA picks up the hydrogen, it can pick either this hydrogen as well as this hydrogen, but picking up this hydrogen is definitely not a favorable one, as you are having a sterically bulky group at this site, methyl as well as paratollyl, which is a huge bulky group. So, phenyl selenium is a definitely a bulky reagent. So, expect that LDA first picks up this hydrogen, create the enolate, and then electrophile will be attack in this particular carbon. So, now how you can make this ketone. So, for making this ketone, we are now do a retro which follows a very known Dickman type of reaction. So, this FGI was saying that as a Dickman type of reaction, where you basically use these things to undergo the Dickman cyclization. Fine. Now, I am coming to the starting material, how this starting material can be converted to here. So, now I am trying to do a intermediate, find that if you have this intermediate, this can be easily converted to this diester by a simple oxidative cleavage of this double bond here. Now, from this to this initial starting material is symmetrical one, from this to this is a simple desymmetrization reaction. Now, what we will trying to do? We will now do the forward pathway and see how the synthesis can easily be carried out. So, initial starting material is this, which I say is a symmetrical molecule. So, you do a LDA treatment followed by a TMS chloride, which will basically give you the desymmetrization to give you the enol ether Me para toluene. So, this particular step is your key desymmetrization reaction. So, I say single step desymmetrization is always preferred, and you have now accomplished this single step desymmetrization to create a desymmetric enol ether from a starting symmetrical ketone. Now, as per the retrosynthetic pathway, if you now do a ozonolysis, you will basically cleave this internal double bond and you get CH2, CH2, CHO, CH2, CH2, CHO here, and then this part you will be getting CH2, C double bond to this OTMS ester. So, you have a aldehyde, you have acid or ester. So, what you do first? Oxidize the aldehyde. Now, oxidation can easily be done by Jones condition. Now, Jones condition is highly acidic, that will also cleave this TMS ether. So, what basically you will now end up, you get a para-toluene here and then you get this diacid as the main product. Now, if you analyze this diacid, you basically need to convert this diacid to corresponding dimethyl ester by simply treating with diazomethane. Now, now you will be having methyl para-toluene and CH2 CO2 Me and your this is CO2 Me. So, this is the diester which you have earlier proposed in our retrosynthetic pathway as one of the intermediate. Now, I am saying you will be treating this compound with sodium ethoxide as the base to undergo this Dickman cyclization. So, Dickman cyclization, this is first enol this carbon ion generation attack to this particular ketone. Now, once this Dickman cyclization takes place, we will be getting methyl para-toluene and then you basically get the corresponding cyclic ketone. You do the basic hydrolysis with sodium hydroxide followed by heat beta keto acid, which will immediately decarboxylate to basically give you the intermediate methyl para toluene. Now, as I said, you are having a carbonyl compound flanked with 2 methylene. The most easily abstractable acidic hydrogen will be picked up by 1 equivalent of base LDA 1 equivalent and will react with phenyl selenium chloride. Now, you see the molecule how it will react. It will basically give you the ACPH here, this part will be remain similar. Now, do the sodium periodate treatment, which will give you the selenoxide Ac plus, you have this O minus and then pH. Now, selenoxide elimination, as we discussed earlier, will be now taking place, and the selenoxide elimination by heating you will get a phenyl selenic acid, and then you basically get this alpha beta unsaturated ketone as the product. Now, in this intermediate we have already discussed, you are having a alpha beta unsaturated carbonyl at one end, you are having this methylene group still intact. So, now react with LDA, excess methyl iodide 2 equivalent to introduce the gem dimethyl group here. Your para-toluene and this methyl. So, you are almost close. Now, just do the hydrogenation with palladium charcoal hydrogenation to reduce this double bond by simple FGI, and then you can close the, or you can complete the synthesis as shown here. So, this is your target molecule quiperinone, which was initially given. The key reaction we said is the starting compound was giving to a symmetrical compound, which is this compound. The main reaction we said is a enolization followed by enol ether formation, which is the desymmetrization initially is required to give you the cyclohexane based enol ether, which is ozonolized to give you the ester, which I have earlier discussed. So, this way basically a very simple straightforward retro pathway of a symmetrical molecule can be easily desymmetrized, and then depending on your target structure you can complete the synthesis, but the key focus is basically desymmetrization reaction. The similar line will be analyzing another problem. Here I am saying that the target molecule is basically having this structure. The target molecule is having this structure. You have a angular methyl. The starting material was also given to you for your better understanding. The starting material, now if I write, I have given you this particular starting material. Now, if you see, the starting material is very much symmetrical, very much symmetrical. So, here if you now try to correlate, what are the things you basically need? You need to have a desymmetrization reaction either this end or this end, and then you need to put 2 extra gem dimethyl group. This CO2 group needs to be converted to corresponding methyl. You also need to bring a alpha beta unsaturated this carbonyl functionality. So, initially as I said, the desymmetrization is basically two type of desymmetrization, achiral as well as chiral. Here as we did not mention the stereochemistry, we said okay, we will do a achiral desymmetrization, and there are two OH group which seems to be having equal chemical reactivity. So, what we are trying to do, we will let us do it a very simple straightforward protecting group chemistry to desymmetrize it. We will be using a one equivalent of mom chloride, methoxymethyl chloride with a base diisopropyl ethylamine. Now, as I say, we will be doing the achiral desymmetrization. If you see the molecule, this OH and OH are basically enantiotopic to each other. So, in principle both the OH can be converted to O-mom and will give you a 2 enantiomers, but as we are focusing on only achiral desymmetrization, I will try to put only one OH group as a protected, remaining part of the molecule is similar. So, now we have protected selectively one of the hydroxy group. Now, next if you see, you need to introduce 2 gem dimethyl group. So, the best way you can do it, just simply putting this molecule through a oxidation. Now, how it can be done? You simply do a oxidation by this way, your mom is remain here. Now, I say if you use a LDA and methyl iodide, so initial there is a possibility that you get only this monomethylation. In addition, you are having another carbon which also can be forms a carbon ion. So, you might have a 2 regioisomers, this is basically O-mom, O-mom. You have a 2 regioisomers, either this here or this. Now, these steps needs to be bit careful, you probably can get both of this product, you can separate them out, and this particular product will be required by us as we will be now doing the next round of alkylation. Now, for the out of these two compound, you having a this methyl here and the remaining part, it will be just we will write like this because those parts are similar, and you are having another methyl here. Now, as I said that these two compounds can be separated out. If you can separate this starting material, you further do a LDA mediated alkylation. Now, this enolate is now thermodynamically controlled. So, this enolate, if you allow LDA methyl iodide little bit more time is required to have the thermodynamically controlled enolate formation, enolate, and then you will basically get the gem dimethyl product where your mom is this. Now, in reality, in the final product you do not need this carbonyl group. So, what you simply do? You do a Wolff-Kishner reduction. So, this carbonyl now acting as a redundant functionality. So, your O-mom is remains here. Now, next, as the target molecule having a methyl group here, so the CO2 needs to be converted to its, so that it can be easily converted to corresponding methyl. So, do a lithium aluminum hydride reduction first. So, initial desymmetrization is basically when you do the protection, remaining steps all are basically simple FGI. Now, you are doing a CH2OH here. This is very simple. You have to convert the corresponding alcohol to the methyl just by using a tosyl chloride followed by lithium aluminum hydride, which will give the methyl in the angular position is will give you this compound. So, now we are here and now only task which is remaining, you have to introduce the alpha beta unsaturated ketone this point. So, what you now do basically now take this initial starting material methyl with a mom here, you remove the mom with a H plus treatment, do the oxidation to bring the ketone. Double bond. Okay. Now, if you see, we will be doing a similar kind of reaction LDA PH ACCl. These hydrogens are definitely there, but in close proximity you have this gem dimethyl group. Here you do not have any such steric crowding, the one methyl group is there little bit away. So, now basically you will be getting this ACPH and then you follow the standard treatment, sodium periodate heat, you will be getting the final product which is required. So, in principle what are the key transformation was used here? The first transformation we said a desymmetrization through a selective or selective protection. That was the key thing, selective protection of the chemically reactive, both alcohols are equally chemically reactive. So, do the selective protection and the remaining part is very standard FGI, we did standard FGIs. So, in principle this kind of transformation can effectively be very usefully done if you just do the selective protection. Now, this selective protection now we are trying to highlight as a desymmetrization of the equally reactive 2 hydroxy group, which can be desymmetrized. As a starting material is symmetric, you can desymmetrize it through a selective protection. Next, we will be having the problem which probably we have already discussed. I am saying that you are having this alcohol. Now, this particular 2 substituted 1,3-propanediol we already earlier explained, as you are having a plane of symmetry here, this hydroxy and this hydroxy are enantiotropic to each other. I am saying that you need to do a desymmetrization reaction by a benzyl formation. Now, in reality you can do this reaction by numerous way, means you just do a selective stoichiometric based protection. As I said earlier, if you can react with this compound with sodium hydride and one equivalent of benzyl chloride, you will get a monoprotection. And then we also explained earlier, if you go through the slide, if you make the corresponding benzylidene acetal of this compound and react with a hydride source like dibal, it also can be give you this cleavage of this benzylidene acetal. Now, these things are already known to you. Now, what I am trying to do? I will trying to give you another reaction whether this is also feasible or not. I am saying that as this compound is only having a allylic part in one of these main functional group or appendage. So, what I do? I am just trying to see that I am be treating this compound with iodine. So, this iodine will basically give you a iodonium ion first, and then this compound is having two equally reactive CH2OH, which basically act as a nucleophile. Now, these nucleophiles will normally try to react in a intramolecular fashion to open up this iodonium ion, and then what you get? You get 1, 2, 3, 4, 5 member ring as the main product. So, initially after this ring closing, this CH2OH will remain similar, okay. And here you are closing this ring here 1, 2, 3, 4, 5, and you basically get a CH2I here. So, the molecule has been desymmetrized, but our target is you have to bring the allyl functionality back with the OBN remains. So, we will now draw the structure again. So, this compound is basically a tetrahydrofuran. Now, I am saying that now let us do this protection benzyl bromide. Now, you may ask that, sir, why you require so many long steps, because these compounds can be easily made through a single step as a step A and step B. But I am saying that okay, we will just explore some couple of new reactions. Now, what I am saying, if this compound is iodo compound, if you treat with simple metallic zinc, now metallic zinc has a strong affinity to this iodine, and deiodination will takes place. Now, once this deiodination will takes place, it basically initially can give you a zinc iodo species, and then it will give you a some kind of radical or electron deficient species CH2 basically. Now, this CH2, this radical will try to fragment in a different way. Now, this radical will try to fragment because it is having a oxygen functionality in its close. So, you will get a double bond here, OBN, and you get these things. So, this is the reaction which you are basically saying that is a main reaction which is responsible for the desymmetrization. Now, what you need? Simply water treatment to quench the O dot, OH and your OBN. So, though there are multiple steps involved. So, now we will be again coming back the initial problem which was given to you. You having this CH2OH starting material, symmetric starting material. The product which I am requiring is this one. I said it can be done by sodium hydride, benzyl bromide, by one equivalent stoichiometric, it can be easily done. Okay. Next, I am saying that this one also can be done by making corresponding benzylidene acetal followed by acetal cleavage or acetal opening through a reductive way by Dyball. This is also very well feasible. The next one which I just now did, the transformation which you require a iodocyclization by basically making a iodonium ion, then you intramolecular SN2 reaction, with one of this alcohol group, then we did a benzyl protection. So, this part is simple. Then we do a zinc mediated deiodination. So, this the fourth reaction, this one probably is the most crucial reaction which gives you the thing. So, three possible pathways can be formulated for this transformation, and eventually you will find that this step is probably a single step reaction, one step only. You can have a two step reaction here in the step B, and for this root 3 or root C you have 1, 2, 3, 4, it is a 4 step. So, definitely from a cost effective manner the step 1 is preferred, then step 2, but step 4 also very useful reaction, and eventually this also give you the required desymmetrized product which also is your target molecule. So, this way basically you can think about a desymmetrization reaction, and particularly the key transformation which can be thought of. You can basically in principle do a different or you can use different key transformation as your main tool, and then you try to correlate that how this target structure can be correlated back to your static material. We have shown that 3 different routes are possible, and all the routes having their own key transformation. Definitely the route 1 as it is single step, it is normally preferred, but the other routes like route B where you do a reductive cleavage can also be done, and route C is unique because you have some new reaction which will definitely give you a access of the target molecule. Now, we will stop the desymmetrization strategies here, and next we will be trying to give you a idea about the stereochemical strategies which we will next discuss. So, till then just go through the desymmetrization strategies lecture notes, and we will update some of the we will upload some of the assignments, try to solve those problems. So, till then have a good time and goodbye.